Hello and welcome to Man in an Elevator. Right, what am I going to be doing? Well, I'm just going to be going up and down this elevator and talking to you a bit about the dynamics involved. So I'm around about the ground floor. Let's go right up to the top floor, shall we? So what's happening? There's some acceleration going on and it stopped. Now we're moving at constant speed. And then what's going to happen? Feel the deceleration? Now I've stopped. I'm where I want to be, which is on the top floor. Right, let's just close the door, shall we? Get a bit of privacy. So, how did I know what was going on without actually looking at the floor number? Well, I could feel the forces that are acting inside the lift, you see. I'm going to set it off again, which means the door might just open. Okay. There's an acceleration period, I just felt it. So I can feel the force through my legs. Now we're at constant speed again. And then it's going to be a little bit of a wait till we get to the bottom. It's a good few seconds, wasn't it? How was that silence for you? I hope it was good. Anyway, there we go. Slowing down, deceleration, filling my legs, and we're stopping. Right, let's just close the doors again. Cool? Yeah, close the doors. Right, why is this important? Because motion in an elevator is a common examination style question. Okay? You need to be able to answer questions involving forces, accelerations, and time taken for someone maybe to get from the bottom ground floor to the top floor. I've got a scenario for you, which I'm going to put on the board for you right now. Okay, let's have a look at the question then. Man travels on a lift. Starts from rest on the ground floor. I don't know if you noticed, I wasn't always on the ground floor. There was a floor below the ground, but I'd use that just so it gave me longer to explain in the elevator. Anyway, ground floor moves vertically, come to a rest. Again, on the top floor, 27 metres. I don't know if it's 27 metres, could have been more, could have been less, I don't know. The lift initially accelerates at a constant rate of 2 metres per second squared until it reaches a speed of 3 metres per second. Then moves at constant speed 3 metres per second for t seconds. Finally, it decelerates for 2.5 seconds before coming to rest again. This is what your speed time graph looks like. Okay, I mentioned trapezoidal. So here we've got time. And then here we've got, it says speed, but we usually use V, which stands for velocity, but it says speed, doesn't it? Now, this is the constant acceleration phase, straight line for constant acceleration, and then this is the constant speed phase, and then this is the constant deceleration phase, hence trapezoidal. The information we can fit on is that we know that the constant speed is 3 meters per second, okay? And the initial acceleration phase is 1.5 seconds. We know that it was going at constant speed for t seconds. There it was, there, okay, constant speed for t seconds, and then deceleration for 2.5 seconds. So that's it, that's your speed time graph. Now what can we do with that? We can use the fact that the total distance was 27 metres. So all of this area is 27 metres. Now it's been divided up into triangle, rectangle, triangle for your ease of calculation for the area if you want, but I tend to use the formula for the area of a trapezium. Okay, and so the formula for the area of a trapezium is a half times by the base, and the base is that plus that plus that. Okay, so 1.5 plus 2.5, just 4 plus that, so 4 plus 2. So that's the base times by the height. Now this distance there is going to be the same as that bit, so that's also t, and then multiplied by the height, and the height of that is just 3. Happy with that? So area is half of that plus that, the sum of the parallel sides times by the height, and total distance of 27 metres. That's what we need to find. We need to work out the value of t. So what I'm going to do, I'm going to divide by 3 to get 9, double it to get 18, and then I'm left with 2t plus 4 is equal to 18, subtract 4 is 14, divided by 2, t is equal to 7. 7 seconds. Okay, so we've done. We worked out the value of t. So that's part A and part B done for you. Okay. Well, how do you feel about that then? Okay. Well, basically, the motion that we need to do for the first few questions is about what's going on. So let's just start the lift off again. Right. There's an acceleration period going on. Okay. So accelerating constantly until we get to a constant speed. Now a constant speed. Okay, so on a graph it looks like a flat horizontal line. And then towards the end, when we're getting towards our destination, there's going to be a deceleration. So it's going to be your simple trapezoidal graph that you'll be drawing. That's it, the graph of a trapezium. Okay, next bit you need to work out what the acceleration time graph looks like. Here it is. Okay. Now remember it's constant acceleration, so only horizontal lines are needed. Now, technically I suppose if this was a real life situation, like it was a minute ago, wasn't it? I was in an elevator. The acceleration graph would look something like this. Okay, it's a gradual, constant increase and then decrease. Okay, but in terms of our M1 exam, an acceleration graph looks like this. So you've got 2 meters per second squared for the initial acceleration phase, and then you've got no acceleration when it's in constant speed, and then you've got a deceleration. Okay, that's what your graph looks like. You don't need to work out what this is, but I'll just show you how to do it. If I just go back to this bit here, now we were given that the acceleration there was 2 meters per second squared, you can work it out the same way you work out the gradient on a graph. Remember, the acceleration is the gradient on a velocity time graph. So if you work out change in height over change in horizontal, 3 divided by 1.5 is 2. Here you just do the same. Okay, so the change in height for this bit is 3, and the change in the change in horizontal for this bit is 2.5. So 3 divided by 2.5, easy enough. Just double top and bottom, you get 6 over 5, so 1.2. Just remember, because it's downwards, it's negative, so that would be negative 1.2 meters per second squared. Hence, this bit here. Now, while you didn't need it for this part of the question, you will need it later on. The next part is just an acceleration graph, which is quite straightforward. As I said, there's an acceleration period, constant speed, and then deceleration period. Now, the deceleration period, of course, is negative acceleration. So in your graph, you're making sure you put that as negative. Okay? So, back to the classroom. Have you noticed how I'm wearing glasses in the classroom and no glasses in the left? It's kind of like Superman and Clark Kent, isn't it? Obviously, minus the good looks of Superman and Clark Kent. Which always seemed to be ridiculous to me that people could know, the audience, that Superman and Clark Kent are the same, but people in the Superman world couldn't, okay? Just by removing glasses, hey, somebody different. It's almost like the Robin scenario, isn't it? Okay, Robin puts on a mask, which is as good as glasses. Suddenly, whoa, who is this guy? Unknown, Caped Crusader. Anyway, Batman, you can get away with it, okay? Because he's got a full-on cowl, doesn't he? Okay. Then Iron Man, there you're talking, because you've got an actual proper mask. But people know who Iron Man is. Isn't that just so ironic? Okay, the one with the full-on mask, Iron Man, and people know who he is. Okay, whereas with Clark Kent glasses, he's not Superman. Oh, now he is. Anyway, back to what I'm supposed to be doing. Okay, I like this bit. The mass of the man, 80 kilograms. Again, no. It's just for show, really, what I'm doing. And the mass of the lift is 120 kilograms. Okay, the lift is pulled up by means of a vertical cable attached to the top of the lift. By modelling the cable's light and inexpensive, we'll find the tension of the cable. The lift is accelerating. Now, for finding the tension of the cable, we've got to consider the whole thing. This is sometimes called the whole system. Okay, the system as a whole, which includes the man and the lift, man and the elevator. Okay, so altogether, consider the combined mass. Okay, 120 plus 8, that's 200 kilograms. So the weight then for the whole lift is 200 G. Okay, and then the tension is what we've got to find. Now, when it's not moving, the tension and the weight have got to balance each other out. Okay? When it's not moving, tension and weight balance each other out. Okay. Now, the thing is moving though. There's an acceleration. So put the F equals ma there as a reminder that the total force must be the product of the mass and acceleration. And the acceleration is 2 meters per second squared in the initial acceleration phase. Total mass is 200. Therefore, the total force has got to equal to 400. Now, what's going on? Because it's moving upwards, because the upwards direction has been positive. So upwards, we've got this force, the tension, the string. It's the only other force that's there. We're obviously modelling this as the only forces of tension and the weight. Tension, subtract 200 G, that must total 400. Okay, so put this onto the other side. 200 G is 1,960, out to 400, 2,360 newtons. So the total tension is 2,360 newtons. Okay. Now, here's the part I really enjoy, the bit about forces. At the moment, the elevator's not moving, it's stationary. Okay, I've got the door closed. Okay, but what's happening? You've got tension in the cable above, to prevent the lift from falling. Okay, obviously there. And you've also got the combined weight of this whole elevator and myself as well. I'm not actually 80 kilograms. I'm not 80 kilograms, believe me. Okay, but maybe it's close enough. Okay, it's about 70 something, who cares? Anyway, combined mass of this elevator and me could be about 200 kilograms, say. Okay, what that means is because we're stationary, then the tension in the cable has got to match the weight, the total weight acting downwards. Okay, remember the cable has got to carry me as well as the elevator. Okay, if I get off, then the whole mass of this system is lower, isn't it? Okay, so in a scenario such as this, when we're actually accelerating, certain forces involved, and we're trying to find a tension in the cable, we've got to consider what is the total weight of this combined system. Okay. Right, now we come to the last part. Okay, find the magnitude of the force exerted by the lift on the man during the last 2.5 seconds of motion. Okay, so last 2.5 seconds of motion, lift is decelerating. Okay, remember we worked out what that acceleration was earlier. That acceleration is negative because it's decelerating 1.2. We've got to make use of that in the F equals ma equation. So the acceleration is negative 1.2 meters per second squared. Now this is a different scenario. This isn't tension anymore in the lift. This is about what the forces are acting on the man. So we've got to consider the man inside the elevator. Okay, now what's happening with the man? The tension is not attached to the man. Tension is attached to the lift. Okay, so what force is acting on the man? What's the normal reaction of the fall? The reason the man does not fall is because he's standing on the floor. Okay, which is normal reaction force. Okay, and of course the weight of the man is just 80 g. Okay, just the man this time. So if we consider just the man, 80 kilograms, so 80 g is the weight downwards. And there's a normal reaction force acting upwards. Okay, if this system is not moving, if the elevator is stationary, then these two balance. Okay. And the normal reaction is just 80 times g, which turns out to be 784 newtons. If it's in constant acceleration mode, okay, then again, constant speed mode, I meant to say, constant speed mode, acceleration is 0, again, these balance. However, when it's moving, things do change. Okay. In this scenario, so you've got A is negative 1.2, so mass times acceleration, that side is going to be negative, of course. But then when you consider the total force acting is R subtract 80g, and it's moving upwards, even though it's slowing down, R subtract 80g is equal to negative 80 times 1.2. You'll see that this reaction force acting on the man is actually lower. Okay, I want to talk to you about how the forces change when the lift is in motion. At the moment it's stationary, so that means the forces must be balanced. So weight must balance with the tension. So if I'm 80 kilograms, which I'm not, if I'm 80 kilograms, weight downwards is 80g, and then that's got to balance with the normal reaction upwards. Okay. Now, if I set this moving, I'm going to go up to the top floor. There's an acceleration period. Okay. I can feel the force through my feet. Okay. There's an extra force upwards, and if you calculate the normal reaction force now, it's going to be more than 80 g. Okay. And then constant acceleration, force is balanced, weight is same as normal reaction. Then deceleration phase. I can feel the lightness in my legs again. That means there's less of a normal reaction force. Let's just close the door, get a bit of privacy again. Okay. So did you get all that? Basically, when the lift is not moving, then the weight and the normal reaction force balance. Okay? When the lift is moving, forces are going to change. Okay? This is what it looks like on a whiteboard. Let's think of another scenario. Okay? Let's think of another scenario. Suppose this time it's the beginning phase, which was 2 meters per second squared. That was what was happening at the beginning, okay? And it's still moving upwards. Then this would change to R minus 80g is equal to, that would be positive 80 multiplied by 2 instead. Let's see if I can do this numerically without a calculator. Of course I can. You should be able to as well, okay? So 80 times 2 is 160. So that's going to be positive, isn't it? 160. And bring that over to that side. You've got effectively weight, which is 784 newtons, added to 160. It's going to be more, isn't it? It's going to be 800, 944. Okay, 944 newtons. The reaction force is actually more during the acceleration phase. Okay. Now in the elevator, when it was going upwards, I felt the force acting on my legs as we're actually moving upwards. I felt something pushing me. Here, you can see mathematically, that's because suddenly this reaction force has increased during the acceleration phase. When it was not moving at all, when it was stationary, it was just that. I didn't really feel anything. You don't. When you're just standing still, like this, you don't feel any force. but suddenly when you're in an elevator and you're moving upwards, you feel a greater force. Okay, so obviously the reaction force has got to be bigger. Okay, if I just get rid of that and put it back to how it was during the deceleration phase, you feel lighter. Okay, because you're slowing down, you do feel lighter. Hence, that reaction force is actually lower. Okay, I'm hoping you got something out of that. Okay, back to the elevator. Well, that's it. That's my question. That's my elevator question for mechanics. I hope you enjoyed it. Okay, just don't try this at home. Go to an office block. Far more fun. Of course, you can't try it at home. Right, I'm off. See you later. Got to teach some maths.